All right, moving on to scalar multiplication with vectors. Let's see what we've done so far. Let's do a quick review. So far we've talked about vector addition and subtraction, how to do these operations with vectors. And we've done it two ways. We've done it geometrically, that is where we take a vector such as this one, and then we add those two to create a new vector, right? So we know how to add vectors geometrically. We've done it algebraically if I know the components, okay, where we know the components, right? So if I know the components of this vector and add it to another vector or subtract it to another vector, I know how to find the resultant vector, right? So we're pretty familiar with addition and subtraction. Well, what about multiplication? Okay, so with vector algebra, there are basically three types of multiplication. You can't just do this times this, okay? Because a vector is an object, it's kind of like an arrow, okay? You can't just multiply arrows together, right? It doesn't make sense. So what you can do though is you can do scalar multiplication, which is what this video will focus on. And just as kind of a introduction, there is something called a scalar product or a dot product, and a vector product, which is a cross product. Okay, both of those are these are synonymous. Okay, but we're for this video we're only going to be focusing on scalar multiplication. But you can keep these in the back of your minds as you watch this. Okay. All right. So let's go into scalar multiplication. What is scalar multiplication? Okay, well we know what scalar means. Scalar means a quantity that only has a size or a magnitude. It does not have a direction. Okay, so a number like 1 or 2 or -4. Okay, any of those are scalars. Well, let's think about. Let me back up a little bit and introduce to you. How scalar multiplication works. Okay, if I have a vector A, and let's say this vector A has the components of 1 and 1. Okay, so it's 1 this way and 1 this way. All right. If I were to line them all up in a row, then I would end up with three vectors that are basically the length of A, right? So I would have A plus A plus A. This vector here would really be A plus A plus A. Another way I could write that would be 3 times the vector A. Okay, so that's what I'm doing. This is just scalar multiplication. All right, very simple. All I'm doing is I'm taking a vector and I'm multiplying it with a scalar value. Okay, so this is the process of scalar multiplication of a vector. And when I do that, let's look at the components. What's going to happen to the components of this final vector? This is going to be 3a, right? Well, this vector is going to move over 1, 2, 3, and up 3 times as well. Okay, 3 units. So this would also be 3 and 3. So notice the change. I went from 1, 1. When I multiplied it by 3, I went to 3, 3. Okay, and this can go also. This works also with negative vectors. So if I was going in the opposite direction, okay, if I had minus A, and minus A, okay, well that looks really messy, but you get the idea. Okay, if I did that and this was a negative number, this would also have to be, each of these components of my original vector would have to be multiplied by the scalar. So that's scalar multiplication, very easy. Okay. If you want to write that down in your notes, you could say scalars have a size but no direction. They look like this. And so when I do 2 times a scalar times a vector, I am multiplying a vector with a scalar. And here's the key point, okay? Scalar multiplication always results in a vector, okay? Multiplying a vector with a scalar will always result in another vector. Okay, so if somehow you do your math and you end up with a single number, a scalar quantity, you know you've done something wrong. Okay, and that's important for later on when we talk about the dot product, but for now, if I do scalar multiplication, I will always get another vector. Okay, And here's kind of the generalized form of this. In component form, if k is a scalar and I multiply k times a vector, that new vector that's formed will have the components of k times the component times the original components. Okay, k times a1, k times a2. All right. So let's do one example here. Given r is 3, 2 and s is 2 minus 2, what is 2r plus s? Okay, so what is 2r plus s? Well, let's just use substitution here. I have 2 times 3, 2 plus 2 minus 2. Okay, that's really what I'm doing here, isn't it? Okay, so what would happen to this term right here? Okay, this should result in another vector, right? And then I'll be adding a vector plus a vector. So I should get another vector, really, in my final answer. So I'm going to carry this through, and I get 6 and 4 plus 2 minus 2. And now it's really easy. It's just going to be 6 plus 2. So I have 8, 4 minus 2, which is 2. So that would be my final vector that would be the equivalent of 2r plus s. Okay? And you could do this geometrically too. If you wanted to graph this out and check it, you would see that this is true. Okay? If I take 2 r's and then add an s, I don't know if that's the form, I would end up with something like that. Okay? That right there should be that. Okay? But of course this is not accurate at all, so let's just erase that. Okay? All right. Let's do one more example. Sketch any two vectors p and q so that, or such that, p is twice the length of q, twice the value, the components of q, right? Okay, so let's start by defining what q would be. Let's say q is this. Now, what would be to q, right? Very easy. I would be putting them in a row. Okay, so there's q, and there's q, and my final vector would be p. Okay? And last but not least, let's try one more. P, if I had q here, what would be p? What would the vector p look like? It would be half the length of q, so it would probably be this. Okay? There you go. That's it for scalar multiplication. And you can go to Schoology and check your homework. All right.